All right, our next speaker is Kicha Chai. He is affiliated with Cornell University and unfortunately wasn't able to be here, so this is going to be a recorded talk. It's going to talk about proactive data center transport for proactive data center transport protocol. We are ready for the tape. Thanks.
New proactive data center transport that simultaneously achieve near optimal latency for shard flows and near optimal network utilization. Two important goals of data center transport protocols are achieving low latency for shard flows and high throughput for long flows, which essentially means high network utilizations. Our community has been exploring designs for data center transport for almost a decade now. Many great ideas have emerged during these explorations, ranging from reactive transport protocols, where senders react to congestion using congestion signals like packet drop, ECN, or delay, to proactive transport protocols, where hosts proactively avoid congestion using admission control and packet scheduling. dcPIM is a proactive transport design. Past research on proactive transport protocols has led to four principles that enable achieving near optimal latency for shard flows. First, shard flow should be transmitted as soon as they arrive, minimizing the waiting time at host. Second, shard flow should be prioritized both at the host and in network. Third, perpetual load balancing should be used to reduce in-network contention between shard flows. Finally, fast loss recovery mechanism can enable further reducing shard flow latency under extreme in-cache scenario, where shard flow packets may be dropped despite high priority. For example, NDP used a fast loss recovery mechanism by exploring a specialized hardware design. dcPIM embodies all these principles within its design to achieve near optimal latency for shard flows. While we know how to achieve near optimal latency for shard flows, one question remains: can we simultaneously ensure optimal network utilization? Achieving the two goals simultaneously is far from trivial. I will highlight three problems. First, as mentioned earlier, when prioritization is used, long flow may be blocked due to high priority shard flows, both in network and at host. Indeed, if low latency is more important, such a blocking is fundamental. The other two problems are more interesting. The second problem is that long flow may contend with other long flow inside the network. Even when using perpetual load balancing, long flow may observe transient contention. For example, when network topology are oversubscribed, ideally, when such contention happens, we want to ensure that the contending flow quickly converges to the rate, such that the sum of the rate is equal to outgoing link bandwidth. For instance, in this figure, one ideal solution is for the two flows to quickly converge to a rate equal to half of the egress link bandwidth. The third problem is more fundamental. In existing proactive transport design, contention between long flows at host. For example, for receiver-driven transport protocol like p-host, under an outcast plus permutation traffic matrix, all receivers may end up sending tokens to the same sender. This would result in suboptimal network utilization, since the sender can only respond to one token. One may imagine protocols like HOMA that use overcommitment, where each receiver can send multiple tokens per M2 transmission time, may resolve the above problem. However, that's not the case. Consider the figure on the right, where the workload is a mixture of the in-cache and permutation traffic matrix. Here, even if each receiver can send tokens to multiple senders, network may be underutilized, since each sender may end up sending data packets to the same receiver. The core problem here is that in existing proactive transport design, senders and receiver make uncoordinated decisions and thus cannot avoid network underutilization. dcPIM resolved the challenge discussed on the previous slide using the idea of matching. Let me provide some intuition about the matching first. The ideal solution of the prior example is to ensure that each sender sends a long flow to a unique receiver. This will minimize long flow contention at the host, thus maximizing the network utilization. Each sender sending a long flow to a unique receiver and each receiver receiving a long flow from a unique sender is referred to a matching between sender and receiver. Intuitively, given a set of flows, the more senders receiver pairs are matched, the higher network utilization will be achieved. It turns out that the matching have a long history in computer networking. For example, almost all switch fabrics internally use matchings to schedule packets from input ports to output ports. The key insight of dcPIM is that modern data center networks bear a striking similarity to switch fabrics. Both use network topology that are organized in a cross-like structure using low-pole current switch, and both of them experience similar workload permutation, incast, outcast, and out-to-out. dcPIM explores the similarity to design transport protocol that extends super optimal switch scheduling mechanism to a data center transport. dcPIM integrates the extension of the super optimal switch scheduling mechanism with principle from prior proactive transport designs to simultaneously achieve near optimal latency for sharp loads and near network utilizations. In this talk, I will focus on the core dcPIM contribution, achieve near optimal throughput for long flow using a matching-based transport design. dcPIM plays its intellectual roots in PIM. PIM is a distributed matching protocol, variation for which has been widely deployed in switching fabric. Suppose we have a workload as shown in the figure, where nodes represent ports in the switch, line represent packets, there are endpoints. For example, a switch may have 64 to 256 ports. Initially, all ports are unmatched. The way PIM works is that it exchanges multiple rounds of control plane message between input and output ports to compute a matching between sender and the receiver ports, and then match sender and the receiver port exchange data in a data transfer phase. Each matching round roughly takes 1 RTT, with typically picosecond scale in switch. The widespread use of a PIM and its variant in switch fabric is due to several interesting properties of a PIM. It achieves near optimal throughput using log n rounds of matching without requiring any specialized hardware. PIM also utilizes a randomized algorithm, which is robust against worst case input and admits a simple mathematical analysis. However, simply using PIM on data center network is challenging. While PIM can compute near optimal matching using log n, maybe 8 rounds, each requiring a few picoseconds before transmitting data, data center network will require prohibitively many rounds due to much larger number of hosts in data center and microsecond scale RTT before transmitting data. We need new techniques to avoid loss of utilization due to larger scale and larger RTTs. dcPIM extends PIM to account for larger scale and larger RTT for data center networks using 4 core ideas. dcPIM presents a new theoretical analysis of a PIM, which shows that the traffic matrix typically observed in data center networks enable dcPIM to compute near optimal matching using constant number of rounds. This enables dcPIM to achieve near optimal network utilization independent of the data center size. dcPIM uses a normal distributed protocol that the pipeline matching and the data transfer phase, thus hiding larger RTT in data center networks. dcPIM also allows each sender and receiver to match with multiple receiver and sender. This enables dcPIM to handle multi-hundred gigabit links or larger roads. To achieve high network utilization, even when long flows contained inside the network due to oversubscription, dcPIM uses a token clocking mechanism that's similar to p-host or TCP. This mechanism ensures that at all time, hosts have exactly 1 BDP worth of packets in flight, exactly what's needed to keep the network utilized for 1 RTT after the congestion is resolved. In this talk, I will focus on the first 2 ideas in dcPIM. The key technical contribution of dcPIM, the new theoretical analysis of a PIM. Essentially, this new analysis establishes the relationship between the number of matching rounds, the matching size, and the traffic matrix sparsity. Consider a network with n hosts. Let m star be the matching size computed by the PIM protocol of the log n round, where alpha is some constant between 1 and n. Let delta be the average number of active flows per sender across the data center. Note that the alpha averages the number of flows across all the senders. Then, using R round, dcPIM computes a matching size as shown below. This result is interesting. Many real-world traffic studies show that the average number of active flows per sender or receiver is a small constant. For example, prior work showed that across 7 different data centers, the average number of concurrent flow is less than 5. For such sparse traffic matrix, the above result shows that it's possible to compute near optimal matching using an extremely small number of rounds, independent of the data center size. For instance, when delta is 10, dcPIM computes near optimal matching using 4 rounds. Even for delta as large as 50, dcPIM computes near optimal matching using 5 rounds. The new theoretical analysis in dcPIM demonstrates that near-optimal matching can be computed using small number of matching runs. However, PIM-style protocols where data transfer happens after matching runs can still lead to underutilizations. dcPIM explored the fact that data center networks are rarely run at an average load of 100%, thus providing enough bandwidth to simultaneously send data and control packets. Especially, dcPIM pipeline the current data transfer phase with a matching phase for the next data transfer phase. To ensure that the matching quality doesn't degrade with pipelining of a matching and data transfer phase, dcPIM gives high priority for control packets, even for large data center network, prioritizing control packets over data packets combined with modern switch buffer size ensure that the control packets experience a lossless channel in failure-free scenarios. I will have no time to describe several additional ideas in dcPIM, for example, handling in-network congestion, fast loss recovery, extension for multi-hundred gigabits link, and a completely asynchronous design. Please see the paper for more details. We have evaluated dcPIM across a variety of settings that mix-match 3 network topologies, 3 workloads, 3 traffic matrix patterns, 2 oversubscription ratio, and varied network loads. I will give you a glimpse of dcPIM evaluation results over leaf-spine topology with 144 hosts, 100 gigabit links, 4 bisection bandwidth, IMC10 workload, and various traffic patterns. Throughout our evaluation, we find that dcPIM can sustain high load. For instance, for this setup, we find that dcPIM can sustain network load as high as 0.84, while other protocols cannot sustain 0.8 load. As I will show you, this is due to the matching-based design of dcPIM. Let me discuss some interesting observations related to the sharp load latency first. We use 0.6 load for this graph, since all protocols were able to sustain this load. NDP has sharp load latency because it does not use prioritization mechanisms, and it proactively draws packets, causing frequent retransmission. HPCC keeps low latency of sharp load by ensuring small amount of buffering at each switch. However, enforcing Z buffers being near empty at all times results in reduced throughput for long flows, as we will see soon. HOMA doesn't handle in-network congestion. HOMA Iolus extends HOMA to handle in-network congestion. HOMA Iolus can sustain good loads, but has higher short roaming and tail latency. This is because both HOMA and HOMA Iolus don't have a fast loss recovery mechanisms. dcPIM achieves near-optimal sharp low latency by incorporating idea from all prior proactive transfer design. dcPIM allows sharp loads to be transmitted immediately upon arrival, carefully assign packet priorities, using per-packet load balancing to minimize in-network contention, and use a fast loss recovery mechanism by exploiting the fact that control packets observe a lossless channel. However, unlike NDP, dcPIM doesn't require any specialized hardware. Large-scale simulation often hides how protocol handles short-term traffic bursts. To demonstrate the behavior of existing transport design during the contention between long flow, we use micro-benchmark. Here, I present 2 results. On the same 2-tier leaf-spine topology as earlier, we have 16 senders sending 1 flow each to 16 receivers in the other tour. And every 100 microseconds for the first 600 microseconds, 50 other senders send 158 kilobytes flow as an in-cache traffic to one of the above receiver. We observe that for this workload, HPCC is stubborn due to frequent triggering of a PFC. HOMA Iolus and NDP converge to the relative good utilization, but it takes 300 to 600 to converge. This is because these protocols have no way to coordinate between central receiver, resulting in long flow contention and host. Exactly the problem I discussed earlier. dcPIM matching algorithm operate at the tenth of a microsecond. Thus, it's not only converge quickly, but also achieve high network utilization by computer good matching. Our second micro-benchmark further demonstrates the severity of the problem due to poor matching in prior designs. Here, each of the 144 senders have a long flow to send to each of the 144 receivers. The existing protocols actually achieve low utilization for this workload and take a long time to converge. dcPIM is still able to achieve high network utilization using its matching-based design. Note that for larger n times n dense matrix, dcPIM may not converge to optimal matching, but this may be real since data center network have a sparse traffic matrix. In summary, dcPIM is a proactive data center transport design that simultaneously achieves near-optimal latency for sharp loads and near-optimal network utilization. dcPIM achieves this using a matching-based design that extends classical switch scheduling protocols to a data center transport. dcPIM is open source, and all the documentation necessary to reproduce all results discussed in the paper are available at the dcPIM GitHub repository. Thank you.
Awesome, thank you. Yes, we have Kicha live. Are there any questions? Yes, thank you.
Hi, Anja Feldmann from Max Planck Institute for Informatics in Saarbrücken. My question is, in order to do your matching, you need to understand the traffic matrix. How are you actually estimating the traffic matrix? And how do you deal with rapidly changing traffic matrices?
So this is an easy question. In a sense, there are multiple ways. The first way that I mentioned in the paper is once the flow arrives, the sender will send the notification packets to inform the receiver, hey, I have a new flows. And based on this information, then the matchings can happen. Or essentially, the second way I can imagine is the sender can essentially can initiate the matching because it knows all the traffic matrix per sender. Do I answer your questions?
I guess this assumes that the sender knows how much data it wants to send, but that is typically unknown when you actually start a TCP connection. So how do you deal with that?
I see. That's a great point. Again, there are two ways I can imagine. One is you know the flow size, and if you don't know the flow size, however, you can still do the matching. The trade-off here is maybe in the data transmission phase, a flow has been finished, so there might be some bandwidth being wasted at some parts of the data transmission phase, and this is the trade-off we have to make.
So in your evaluation and in the results that you showed, what kind of knowledge about the amount of data that you're transmitting did these simulations or these evaluations presumed?
I see. So we assume we know the flow size. So the scenario I described earlier didn't happen in our simulation.
Thank you. Another question? Yes, Hari.
Hi, Hari Balakrishnan from MIT. I have a quick question. So I'm curious why you looked at PIM and not iSlip, because I thought that one of the advantages or disadvantages is that sometimes you might get a very high skew in terms of allocation. Is there a reason PIM is a better method to use?
That's a great point. So the main reason we choose PIM is due to its throughput optimal utilization guarantee. Essentially, when we look at iSlip, if I remember correctly, iSlip used some round-robin mechanisms to do similar switch scheduling. But I didn't remember if it provides the utilization guarantee.
I see. And then the other thing is, if you have lots of short flows, I always thought that the overhead of kind of you do the request, and then you do the grant, and then the accept. So there's always like 2 or 3 messages flowing. Do you think that the overhead of that in practice, especially given most flows are short, is going to be substantial?
Great question. So for short flow, we are actually allow them to bypass the matching. So the overhead only goes to the long flows and mid-sized flows. And if you see the figures in our paper, you can see the trade-off here is that mid-sized flows will suffer a bit for the latency because we prioritize the short flows and the long flow transmission. We also prioritize long flow in a sense the sustainable load is very high. So you can see the mid-sized flows, performance will be suffer a bit.
Any other questions? There's one in the back.
Yes.
Please quickly. Thank you.
Thanks for your great presentation. This is Ashkan actually from Canada, Huawei actually Research Center. I'm just actually curious if you applied your approach just on actually leaf spine topology, or have you tried any other topologies like the dragonfly or three-tier actually fat trees? Thanks.
Yes, we actually did in our evaluations. You can check the results in our paper. So we actually run our simulations in fat tree topology with 1024 end hosts. And the result shows the performance is consistent across different topologies.
Thank you.
All right, awesome. Let's thank Kiche one more time.